me that's amazing is with the wildly different assumptions, I would claim that all of these 15 different models are basically close to reality. The middle one, you're looking at the temperature structure of the atmosphere. So here you're looking at height. You're using pressure as a proxy for height. So the vertical axis is the elevation, the height above the Earth's surface, and you have the temperature in absolute temperature. And again, you have a black curve to represent reality, observations made either with balloons, satellites, or at the very bottom, instruments. And you have the 15, or this one is 13 different models. Again, the models differ from each other. But to me, at least, they represent pretty darn close to reality. These models are getting most of what's going on. Then, here's a different kind. Here you have an insult to the atmosphere, and you're modeling what's going to happen. The insult was a volcano eruption in 1991 in the Philippines, Mount Pinatubo. So what you have here is the global temperature change. In other words, a volcanic eruption puts a lot of junk up in the atmosphere, and that junk up in the atmosphere changes the ability of the atmosphere to absorb and radiate energy, therefore is expected to change the temperature in a complicated way. Well, here is the actual change. The black curve is the actual change in atmospheric temperature globally following the eruption. And basically what you're seeing there is the change. In other words, 0 represents no change in temperature. 0 represents the temperature before the eruption. And the dotted line represents, well, there's 2 dotted lines, 2 model results. Again, close. You could say close to no cigar. That's people's opinion. Most scientists would say that's close enough for the cigar. In other words, it appears that the theory is about right. It doesn't have details. It's not going to tell you specific detail. What's the climate going to be in Detroit in the year 270? You're not going to get that from these models. Okay, now prediction. Oh, no. This is still retrodiction. Here's the important point. And now we're getting to the role of human beings. I told you one of the big questions, the political question, or the scientific question, but of course with enormous political implications, is what is the role of human beings? Accepting that the climate is going up, whose fault is it? Mama Nature's fault or ours? Well, of course, that's the usual simple-minded. It's either or. In reality, of course, the scientists would say both of them are involved. The skeptics would say it's all nature. Well, there are the skeptics who don't believe there's any climate warming at all. Then there are the skeptics who say, yes, there is warming, but we have nothing to do with it. Well, here is a situation which should go a long way toward answering that question. What you're doing here is use the model and include or not include the human contribution to the atmosphere's carbon dioxide. And again, because you're using a lot of models, there's a wide range in the final results. But the important point is, this is the model without human, the fancy word they use is anthropogenic effects. That's your fault, using these words. So you have natural forcings, and then you have anthropogenic forcings. The dark is the anthropogenic. Without the gray is purely natural forcings, and somewhere in there is a heavy black line which shows you the actual temperature. It seems to me fairly clear that the model, at least, is telling you humans, you can't plead nolo contendere. You can't plead you had nothing to do with it. Here, so that's of course overall. Here is more local. And again, same point of view. Natural but plus human. Natural plus human. And of course the black line is the data in all these cases. And so you're seeing different regions, you're seeing land, ocean, and it seems to me that it's hard not to believe that human beings have been a significant factor, not the whole factor, but a significant factor in the global warming. You can't avoid that. Now, once you believe the model through retrodiction, then you predict. And again, there's lots of different models, and so all these lines give you different predictions. Here, you're showing the response. Assume that you're going to have a 1% per year addition in CO2 in the atmosphere. That's the assumption. And now you run the model. And you get all that stuff. The heavy line in the middle there is sort of the mean of all the runs. So again, if you're a policymaker, I would base myself on the mean, but always keep in mind the possibility that I could be pretty far off. So, and here you're talking about years from the start. So this is today, and this is 80 years down the line. And you get somewhere between a little over 1 degree Celsius increase to as much as 3.5, with the mean somewhere around 2. So, what does that mean? Now we're leaving physics, and what would such a climate change imply for human beings? Mostly not good. Mostly not good. You find, for example, and let's just take one, health. As things get warmer, let's just consider Africa alone. We know that a good part of Middle Africa is very unhealthy because of insects, malaria, for example. We also know that there are mountains there which are comparatively healthful. The mosquitoes don't get up high. We also know that the mosquito line is going up. As the earth gets warmer, as the climate goes up, you expect to get mosquitoes to march upwards. In other words, the healthful areas are expected to diminish. Africa's in bad enough trouble as it is. I can't see anybody saying, well, I can accept that with no problem. And there are lots of others. Water is going to be a problem, ecosystems, food. You got lots of countries where you got a large population living basically at sea level. What's